In the year 132 AD, during the Eastern Han Dynasty, a Chinese polymath named Zhang Heng unveiled a device that may have been centuries ahead of its time. It did not predict earthquakes. It did not measure their strength. But astonishingly, it could detect them even when they occurred hundreds of kilometers away. This device is known today as the Chinese Seismoscope. At first glance, it looked like an ornate bronze vessel. Around its exterior were 8 dragon heads, each facing a different compass direction: north, south, east, west, and the 4 diagonals in between. Beneath each dragon sat a bronze toad with its mouth open. Inside each dragon's mouth rested a small metal ball. When an earthquake occurred, one of those balls would drop into the mouth of the corresponding toad, indicating the direction of the seismic disturbance. But how could such a device work nearly 1,800 years ago? To understand this, we need to look at both historical documentation and modern physics.
Welcome to SciCuriousID, where curiosity meets science.
Our primary historical source is the Huhan Shu, the Book of the Later Han, which describes Zhang Heng's invention in detail. According to the record, in 138 AD, the device indicated an earthquake to the west. No shaking was felt in the capital, Luoyang. Many officials doubted the device's accuracy. But days later, messengers arrived reporting a significant earthquake in Longxi, precisely in the western region indicated. This would represent the first known instance of a remote earthquake detection system. Now let us consider the science behind it. Modern seismology tells us that earthquakes generate waves. The first to arrive are primary waves, or P waves. These are compressional waves that travel fastest. They are followed by secondary waves, or S waves, which move the ground more dramatically. Even if an earthquake is far away, these waves still pass through the Earth's crust, creating subtle ground motion. The most widely accepted reconstruction suggests that Zhang Heng's device relied on inertia. Imagine a pendulum suspended inside the bronze vessel. When seismic waves pass through the ground, the outer casing would move with the Earth. However, due to inertia, the suspended mass would momentarily remain stationary. This relative motion could trigger a mechanical lever system connected to one of the 8 dragon heads. When triggered, a latch would release and the corresponding metal ball would fall. The internal mechanism was likely calibrated so that movement along a specific axis activated only the dragon aligned with that direction. Essentially, it functioned as a directional inertial sensor. Modern reconstructions by researchers at the Chinese Academy of Sciences have demonstrated this is physically plausible. Experimental models have successfully detected directional vibrations using pendulum-based trigger systems. Importantly, the device did not measure magnitude. It was a seismoscope, a detector, not a recorder. But distinction matters. Modern seismographs use sensors to record amplitude and frequency over time. Zhang Heng's device, by contrast, provided binary information: an earthquake occurred, and it came from this direction. And yet, for the 2nd century, that was revolutionary. It reveals something profound about ancient scientific thinking. Zhang Heng was not relying on superstition or omens. He applied mechanical reasoning. He understood that natural phenomena followed physical principles. This aligns with what we now recognize as empirical methodology. The Eastern Han Dynasty faced frequent seismic activity. Earthquakes were not merely natural curiosities. Rapid knowledge of distant seismic events allowed the imperial court to send aid or assess regional stability more efficiently. In that sense, the seismoscope was not only a scientific instrument, it was a tool of governance. Despite debates about the exact internal configuration, no serious scholar today dismisses the ingenuity of the concept. Nearly 2 millennia later, modern seismology relies on global sensor networks, but at its core lies the same principle: inertia. When the Earth moves, mass resists motion. The principle has not changed, only the precision has. The Chinese Seismoscope reminds us that scientific curiosity is not confined to one era or civilization. If such sophisticated engineering existed nearly 2,000 years ago, how many other ancient scientific innovations have we underestimated? Let me know in the comments, do you think this was truly the first earthquake detector, or could earlier devices have existed that history simply forgot?
Thanks for watching SciCuriousID. Until next time.